All right, should I get started?
Yep, sounds good. Thank you.
All right, so thanks very much, Annie, for organizing this event, and thanks to Gary for the initiative. Um, uh, my name is David Mohaisen, and I'm an associate professor of computer science here at UCF. And today I'm going to be talking about a few of the projects that I have been with my students and collaborators working on here at UCF. I'm going to be spending the time talking at the beginning on the other type of projects that I've been doing, and then I will talk about some specific projects on blockchain security to just give you a high-level idea of what we have been doing here. And so before I get started, a little bit about myself. I obtained my PhD from Minnesota, then spent a few years in the research industry before coming to academia, initially joining SUNY Buffalo in 2015, and then joining UCF in 2017 as an associate professor. I spent a couple of summers at the Air Force Research Lab in Rome, New York, among other places that I spent over time. At UCF, I run the Security Analytics Lab, SEAL, where I conduct research on computer security and privacy with multiple applications that I will discuss today. I also teach courses that are aligned with my research, although recently I had some interests in natural language processing and deep learning in particular, that has in a way shaped and kind of influenced my research work and taste. As for my key accomplishments here at UCF, I developed several courses that I've been teaching here, and I advised several PhD students, 15 PhD students, and 2 postdocs over my academic career, 11 master's students, and a few undergrad students while here at UCF. And so that actually I give the appropriate credit for those who I did work with and who have done the hard work with me, so that they are not really just numbers. Here are the faces behind most of the work. 8 of my PhD students have since graduated, and 2 postdocs were done with their postdoc stints and went to academia as professors. Students who have graduated came with me. Some of them came with me from Buffalo, where others were recruited here at UCF. And the students who have graduated worked on the various topics I'm going to talk about today. But those students ended up with some nice positions in industry, like PayPal, Clear Village, with others going to academia at Wayne State University, Loyola, Niagara, and King Khalid University, and postdocs at Georgia Tech and Texas A&M. 4 of my PhD students, Ahmed, Ulku, Sultan, and Afsa, will graduate this and next year by May 2022. I have also some openings for those PhD students out there who want to work on the topics that I'm going to be discussing today. As well, I've hired 5 more PhD students to work with me starting in the fall 2021. Also, the master's students and undergrad students who have been working with me deserve a big shout out. So just so to give you an idea of what I've been working on, so let me shift gear a little bit and talk a little bit in high level. So what motivates my work is here that I've been doing in the last 5 years is the need for better security for systems by finer understanding of their security, privacy, and safety. And my work is particularly application heavy in the sense that I work on multiple applications, including IoT, software, AR, and VR, and blockchains, which I'll talk about at length, network systems, and social media platforms, as well as machine learning systems. And my work is largely experimental in the sense that we look into measuring and analyzing, as well as characterizing through the modeling, security properties, privacy properties, and safety properties in those applications and domains. And in doing so, we employ a couple of unique takes. The first unique take is automation exploiting advances in representation and learning, which can create efficiencies for securing those systems, particularly unveiling new insights that can be used for their security. The other take that I will demonstrate through our work on blockchain systems is that we rely on measurements so that we can understand systems and how they act in reality as compared to theory, and then shed light on their security weaknesses in a way that we can develop then defenses. In the next few minutes, I will talk about some examples of what my students, collaborators, and I have been conducting. Then I will talk about one major project in more details to give you an idea of what we have achieved so far. So in the first project, the goal has been to analyze and understand IoT software, particularly malware, using program analysis and learning techniques. And what we are hoping to achieve in this line of work is to uncover properties of IT malware and create a sound intelligence that can be used for attribution, and then build systems for this attribution and potential detection of IT malware in the wild. Our approach for this work has been using the program analysis, has been using static analysis tools, which means that we look into the actual contents of a program rather than the execution patterns. And our unique take here is combining multiple artifacts that in a way resemble the execution. And those patterns are actually manually analyzed initially by domain experts to show that they are representative of malicious software behaviors. And those artifacts, if you look into this block here, those artifacts are actually divided into 4 or 5 blocks of categories, namely shellcodes, which are tools for execution of the malware, strings, which are cues to the execution, and graphs, which are basically tools to capture execution sequences, and chains, which is something that we defined ourselves to capture dependencies between endpoints used in the execution of the malware, and functions, which are names left by the authors of the malware to express semantics or high-level semantics of the execution. For the learning part, we engineer and use multiple deep and non-deep learning techniques and algorithms, which are shown to be effective in malware classification and detection alike, with an accuracy exceeding 99% in both applications over those features. And so the work has been funded by AFRL through some initial grants, Cyber Florida through a couple of grants, and then NRF, the National Research Foundation, through a major grant, and some collaborators here from UCF have been on this work, include Amro Award, who since has left UCF to NC State. Okay, the next project I want to talk about looks into modeling distributed denial-of-service attacks on enterprises and web services for defenses. And the reason why we care about this problem in particular is because the DDoS attacks have been very central for many years in the threat landscape. And they are unresolved, unsolved kind of problem. The goal here is to predict attacks attributes before they happen. And those attributes may include adversaries behind attacks, attack severity, sources of attacks, such as network location, organization, or ISN, among others. And our key take here is that a good representation in the form of some initial multi-scale attributes from some annotated initial data, which is fed into a deep learning system, may result into a high quality eventual representation, which is actually verified experimentally. And then this representation would be decoded or used, plugged into predictors to one among multiple possible labels for adversary, organization, or country, network, magnitude, etc. And that kind of intelligence can be then used to make good decisions, intelligent decisions about defenses. The insight itself works, and we get outstanding results. For example, state-of-the-art industry error rates are in the neighborhood of 20%, which is reduced in our case, as you can see here, for less than 1% for many attributes of that tax. And so, this is yet another project that we demonstrate that the capability of learning algorithms into solving some hard problems. Sponsors of this work have been VeriSign, which is my previous employer, through some data sharing, and an NSF grant, that was there for 3 years, and then the previously mentioned NRF program. In the next project, what we look into is authorship, attribution, identification from source codes using deep learning. And so we care about this problem from 2 standpoints. First, from a private standpoint, one would be able to de-anonymize open source software contributors, or some people who contribute to software who wish to stay anonymous, and this is not really good. And from a security standpoint, one can attribute malicious code authors, and this is something good. And so either way, we wanted to be able to identify authors by their authorship attributions. Our key insight here, motivated by the success of our representation for DDoS attacks as well as for malware analysis, is that an initial course feature of segmented code for multiple authors or segmented or non-segmented code for a single author can be converted into a high quality code representation, which then can be converted into some labels of a class for an author. And the idea was implemented using some existing data sets, Google Code Jam, resulting in upwards 90% of accuracy for reasonable number of code segments used for training. But more interesting is that we were able to scale this particular problem for a large number of authors in the neighborhood of 10,000 authors. So you will be able to identify a single label author among 10,000 authors. We also explored mechanisms, given that this problem itself relates to privacy, and so we did not want to really open a warm can without finding a way of addressing it for the abuse. So we explore mechanisms that can be used to thwart this technique through code perturbations as it pertains to privacy, and demonstrated great success in that regard. The work has been supported by NRF and collaboration with Inha University and Loyola University in Chicago, where one of my PhD students has been working there as tenure track assistant professor since last year. In the final project I want to talk about before shifting gear to more technical details about one particular project. This one is not really related to security, but to safety, which are kind of related concepts. And the work here is on detecting and measuring toxic users' reactions to online contents. Here I give an example on the news media that we use for analysis, but the work itself and the pipeline that we build considers other type of domains, including exposure of children to inappropriate contents on YouTube, as well as sentiments of the public to COVID-related news posts to highlight anti-X. And the work is integration heavy in the sense that the insight itself is very important as compared to the technique that is being employed, given that the technique that is employed is a standard natural language processing pipeline. The work was motivated by the highly charged and heated kind of debates that we have witnessed over the past 4 to 5 years here in the US, and we wanted to be able to do two things. The first thing is take toxic users' comments, understand their types, regional and temporal tendencies, and their reactions and the reactions of people to the news stories being covered by the news media. The second goal is to eventually measure moderation and bias towards safety of the public. And so we built this pipeline, which is again a standard NLP pipeline that look into representation, classification, and model evaluation when we instrument this pipeline with pre-trained models for those data. What we have found is that despite the moderation implemented by major companies like YouTube in this case, given that this source of data is YouTube, we are able to detect a large number of such inappropriate contents on this platform with a large number of interactions, including views, likes, and dislikes. And what is somewhat concerning and alarming is that with no exception, as you can see here in this figure, is that with no exception, we find that users like those inappropriate contents more than they dislike them, which warrant further investigation. The work was supported by NVIDIA through their hardware grant support, and NRF through the general support, as well as the lead PhD student who has been working on this problem is supported by the Saudi government through a SACM scholarship. All right, so by now, I hope I have given you a high-level idea of what I've been working on in the past. What I've been actually working on right now is somewhat slightly different. So it's something that I've been spending time on for the building up for the research agenda for this and up to 3 years is 4 different topics that we have significant investment in. And so in the first line of work, which is basically in line with the body of work that I've presented so far, I have 2 directions. And that is particularly maybe interesting for those who want to join us and work with us. The first one is behavior modeling of software using dynamic tools. And particularly, we want to understand the robustness of learning techniques to different types of behaviors. And those works already been initiated here at UCF, homegrown, and we are seeking the funding for that. The second direction, which I will cover in more details in the rest of this talk, has to do with blockchain systems and their security. And in this work, we are concerned with understanding and reducing the attack surface in blockchain systems. The other direction that I not really have a chance to talk about, but we are interested in, is looking into AR, VR over wireless and their associated security and privacy. and in the last direction, which is in collaboration with a couple of folks here at UCF and another researcher from Vanderbilt, we look into the utilization of basically website policy analysis and understanding, that is the utilization of natural language processing techniques for understanding policies, privacy policies in particular, and how privacy policies affect the landscape of security against a breach in the health domain, and how privacy and security together affect the outcomes of the healthcare system. Okay, so with 1/3 of the talk is over, I hope that I have given you a high-level idea of what we are working on. And now let me dig deeper into one particular domain, one particular project that we've been working on in understanding attack surface of blockchain systems. The lead PhD student on this work is Mohamed Saad, who just defended his PhD, and he's joining PayPal Research come July. And another PhD student who graduated a couple of years ago from my group, Ashar Ahmed, and he is currently at Clear Village, but I understand that he will join VMware shortly. And this work is based on various publications in ACM CCS, IEEE ICDCS, IEEE ICDCS 2019, 21, 2019, as well as ICB-C and eCrime. Sponsors of this work are AFRL, the NRF, and an ORC fellowship. So for those who were not following what a blockchain system is, the blockchain ledger, or simply blockchain, is a database, is a data structure containing a list of ordered transactions. And like any database, basically a transaction captures changes in the system state. And also, if you look at the figure, transactions are recorded in blocks and chained through a cryptographic hash function pointing to the previous block. That's the name blockchain. And as a result of the chaining with a cryptographic one-way hash function, blockchains are append only, in the sense that hash functions are one-way, and tamper-proof in the sense that hash functions are collision resistant. So now that we know what a blockchain the structure is like, let's look at what the blockchain system itself is. So a blockchain system is an actuated system by a peer-to-peer network of nodes that share a common blockchain ledger. And to ensure that all nodes have consistent ledger, those nodes execute a consensus protocol, such as proof of stake or proof of work. In the case of proof of work, you require solving a mathematical challenge through some random hashing, and the node that solves the proof first proposes the block, and then finally blockchain systems themselves are meaningless without applications. Applications that put these properties to use are called blockchain applications. And in the example of Bitcoin, such an application has the objective of exchanging financial transactions. In Ethereum, it can be a more complex multi-party computation, such as playing some poker game through some smart contract. So this line of work is about exploring the blockchain attack surface. And we start by a high-level look at what can go wrong in those blockchain systems. And one unwanted security implication would be if the blockchain application rules are exploited to either attack users within the blockchain system, for example, by making them pay a higher fee, or to attack other systems such as websites, users, and cloud operators. The second type of unwanted security implication is if there are inconsistencies in the peer-to-peer system that can be exploited to either partition the network to isolate some nodes or optimize some other basic attacks intrinsic to the properties of the blockchain system, such as the 51% attack, which I'll talk about in a second. We categorize those attacks into two types. The first type we call the attacks associated with the application rules, and we call that the application-specific attacks. And those include in-browser cryptojacking and mobile attacks. And then the second class of attacks, we call them the basically associated with network inconsistency. We call them network layer attacks, and we present in that regard three types of attacks: the general, spatial, temporal, and spatial temporal attacks, and then attacks that exploit certain properties of the blockchain system. Particularly, we'll talk about two of those attacks. So here is a brief overview of some of the research that we have achieved in this regard in the attack surface analysis. We have covered various aspects of blockchain systems, including cryptocurrency analytics, such as price prediction and manipulation detection using network artifacts. Concurrently, we have worked on some security aspects of provenance of distributed audits systems by incorporating blockchain systems in their designs. However, the most focused area of research in our group has been on actually understanding the blockchain attack surface, in which we have worked on application-specific attacks, such as DDoS attacks on the blockchain mempool and in-browser cryptojacking, which I will discuss in a few seconds. We have also basically worked on analyzing the attack related to network irregularities in blockchain systems, including the partitioning attacks, which are going to be central in this talk. And as a result of this final understanding of root cause analysis of those irregularities, we were able to develop hash split attack as well as the sync attack. So in the rest of this talk, I'll talk about, again, those initial works on cryptojacking and DDoS attacks and the detection and defense. Then I will talk about hash split. Then I'll talk about sync attack, and then I'll conclude. So let's talk about the application-specific attacks, namely in-browser cryptojacking and mempool DDoS attacks. And so in the application-specific attacks, we first covered the in-browser cryptojacking. For those who don't know what cryptojacking is where an adversary basically injects a piece of code, a small piece of code in a web server that is served to using some capabilities such as cross-site scripting, and that code itself is served to visitors of this web server, of this website, that then can execute on the client side, on the user's machine, with the privileges of the server. And as the name indicates here, cryptojacking, meaning that this script itself is used for mining cryptocurrencies and then running on the client side without any consent, will be basically used to mine cryptocurrencies on the device. So this is much activity. It's a bad activity. We need to make use of techniques that can detect such an activity and try to eliminate it. And so, in the again in the cryptojacking attack, basically the exploited aspect is proof of work based blockchain systems to target our ecosystem, and the adversary here does the cryptojacking through injecting cryptojacking into a script code in a website or a web server. And so to analyze the prevalence of this problem, as well as to detect such cryptojacking websites, we collected 5,700 cryptojacking websites and conducted both static and dynamic analysis, as well as economical analysis of those websites towards their final understanding and detection. And in static analysis, we conducted the code-based feature and applied unsupervised learning to uniquely identify the cryptojacking JavaScript codes from other forms of JavaScript codes. And for static analysis features, we looked into code complexity and structures. In the dynamic analysis side, we did look into the resource usage profiling, and particularly we looked into three types of resources. We looked into memory, we looked into power consumption, and we looked into network artifacts. And so what we have found is that, among other interesting insights, is that the cryptojacking website or cryptojacking codes in particular are very highly resource intensive, understandable, but what is not kind of trivial to observe or see is that websites do not try to hide their intent, as such, do not really implement any throttling for their operation, and so they are easily detectable with dynamic execution. Finally, by observing the limitations in the existing countermeasures for the problem and capitalizing on our final understanding using dynamic analysis insights, we developed more robust countermeasures to prevent cryptojacking and websites using our network-based analysis. Okay, so this is one work. Another work that we looked into is the mempool DDoS attacks and their thwarting them or their defenses. And so for those who do not know what a mempool, the mempool is the structure that is used in the clients for queuing up all transactions that have not been included in a block or confirmed in a block. And so we, through some analysis, we uncovered mempool DDoS attacks that basically force benign users to pay a high mining fee. And the idea is that, at the time of conducting this work, which as you can see is a little bit dated, 2018, what we have found is that there is a strong correlation between the mempool size and the miner's revenue. So the higher the mempool size, the more the miners collect revenue. The lower the mempool size, the lower the revenue. Which is kind of interesting, indicating that a manipulation in the way that the mempool size is evacuated would allow an adversary to gain a lot of money. And so that manipulation could be in the result of DDoS attack, in the sense that you can throw a lot of junk transactions in the mempool and then basically thwart the actual operation of the mempool. So what we have done is that, to address this problem, we proposed a couple of approaches for defenses. We proposed a fee-based and age-based defense, and as the name indicates, fee-based defense is that to disincentivize this adversary who's flooding the mempool with unwanted transactions. What you do is that you force the adversary to pay a small amount of fee, but then given the adversary would want to really create a large number of transactions, then he will pay a significant amount of fees in aggregate. Age-based, meaning that transactions that are longer in the mempool will be having higher priority for being evacuated from the pool. So what we have found is that the fee-based design achieved a high size optimization, whereas the age-based design achieved a higher accuracy in the detection of the malicious transactions or DDoS-related transactions. Okay, so now moving forward, I will talk about 3 pieces of work in ICD-CS 2019, 2021, and CCS that make up, and some work that is not published that we are planning for submission, again, for CCS perhaps for this year. So that we look into the network layer attacks. We look into partitioning attacks as a basic concept. We look then into the root cause analysis, and then as a result of a final understanding of the root cause analysis, we look into various defenses, various attacks and associated defenses. So the first work that we have conducted in this space was a measurement study on Bitcoin. And in this measurement study, we discovered that this measurement study was done initially by 2 of my PhD students at the time, Sad and Victor. And what they have found is that the Bitcoin overlay topology is somewhat biased in its distribution in the physical world and physical network. Basic understanding of physical network. We're talking about ISPs, ASNs, and so you'll find that the number of say nodes in the Bitcoin network is not uniformly distributed across those entities. And so using this insight, we proposed 3 types of attacks. Namely, using this distribution of geographical distribution of nodes, especially, we proposed a special attack using some irregularities in the current state of the blockchain with respect to the up-to-date. We propose this temporal attack, and then with respect to combination, we propose the temporal partitioning attack. Again, in the special partitioning attack, we notice a high centralization of Bitcoin nodes across asynchronous the terminal systems, and we have found that only 24 ASs hosted half of the Bitcoin nodes out there, and only 3 ISPs intercepted 65% of the mining data by the virtue of being on the path between different ASs. Therefore, the Bitcoin can be feasibly partitioned through a BGP hijack, and we demonstrate that. In the temporal partitioning attack, which is a little more subtle, we found that due to the block propagation and the differences in block propagation to different nodes, which is going to be a central theme in the rest of this talk, notable size of the network is always behind the blockchain by 1 or more blocks. And you look here, more than 10, there are about 10% of the blocks, more than 10, which is in this brown color. 5 to 10 is negligible. 2 to 4 is negligible, but you look at those that are at least 1, they are like half of the network that are behind. And so this makes those blocks, as we will argue later, more vulnerable to malicious miner who, after losing a block race, can basically partition those nodes and cause a soft fork. Finally, we combine those insights together to propose a spatial and temporal attacks, spatial temporal attack partitioning, in which an adversary can isolate the synchronized nodes through BGP attacks and the non-synchronized nodes through temporal partitioning attacks in order to create hard forks with visibility. The key insight here, the novel insight here, is basically in our work, is that we observe this weak synchronization, the temporal aspect of the network, and which was not measured before or reported in the previous work, and we exploit that for various types of attacks. Okay, so again, after observing the weak network synchronization and the partitioning attack, we then explored the root cause analysis for weak synchronization by analyzing the impact of unreachable nodes. And we also looked into the addressing protocols, the block relaying protocols, and the network churn. And our measurement revealed various interesting insights. So first, there is a high centralization network churn in which the synchronized nodes that are responsible for provisioning synchronization depart from the network at a high rate, which is a bad thing. And I'll explain to you why this is a bad thing. As a result of their departure, there is a decrease in the average network out degree, and nodes try to increase the out degree by basically making more outgoing connections. However, there are also weaknesses in the Bitcoin addressing protocol, due to which there is a low success ratio of the outgoing connections succeeding, forcing the network out degree to remain low. And as a result, the network synchronization decreases. Moreover, we noted that the last 2 years or so, due to the churn among the synchronized nodes, has resulted in a significant deterioration of the synchronization. And so to sum up, the two key insights of the root cause analysis were that the Bitcoin network itself is asynchronous, and the second one is that the network synchronization and churn have not been incorporated in the Bitcoin security model, and we explored those for the attacks that I'll describe soon. So to sum up, we have looked into the application-specific attacks, hijacking and mempool, and then we looked into the network layer attacks, Bitcoin partitioning, and we looked into the high-level Bitcoin partitioning, and then the root cause analysis. And so as a result of root cause analysis, we envision two attacks, one that looks into Bitcoin asynchrony, and that is called the hash split. Another one looks into the churn, that is called the sync attack. So let me talk about hash split very quickly. And again, hash split, what it does is that it really exploits the network asynchrony for launching an attack. And so before I get started, let me look into a couple of configurations of a network. So let's start with, say, for example, a bunch of nodes M1 up to M4, and those are fully connected, as you can see here. And so there is a scenario in which we could assume that there is an negligible propagation delay among those nodes. So if a block is generated by M1, the block is going to be sent by M1 and is going to receive in no time by M1, M2 up to M4. And so this is what we call negligible protocol propagation delay, and this would result in the lockstep synchronous network, which is the initial formalization by the original proof of work, and then that was more formally analyzed by Garay et al., which preserves the 51% hash rate bound for majority attack, in the sense that an adversary who wants to force a bogus block on the network on the blockchain has to have 51% of hash rate so that he can actually win a race condition for the block propagation. All right, so this is one scenario. Let's look at the other scenario, which is the non-negligible propagation delay. And so for this non-negligible propagation delay, what you would do is that M1 would send its block, and then the block will take some time to arrive to M2 up to M4. And that is, maybe for some reason to do with M1 and how it is connected to the rest of the network. And so this would result in the non-block step synchronous network due to the delay. And it has been shown by the work of Bass and Dicker that you can reduce the hash rate requirements from 51% that we described earlier to 48%, which is significant if you talk about, from a theoretical point of view, if you talk about the theoretical guarantees of majority voting. Okay, so these are two configurations. Can we basically do more harm? Can we do better? Better in the sense that it's worse for security. And so the idea here is that, basically, the asynchronous network leads to a major security problem when combined with an application-specific rule in Bitcoin. And so the fact that actually you cannot connect to all nodes, you cannot actually have the network fully connected, indicates that a block has to go through multiple hops, multiple nodes to reach to all nodes in the network, and that actually will favor certain behaviors. So in this case, if say M1 is generating a block, it will send it to M2, M2 will send it to M4, M4 will send it to M3, and then you have a synchronous network where miners receive blocks at different times. So considering the network asynchrony, our objective here is to combine both the application-specific rules in the Bitcoin network with the network communication model, which is, again, as we described earlier, to construct a new type of attack that would visibly violate certain properties of blockchain system, particularly the consistency and the chain equality, with a high probability, if we may add. We call this type of attack the hash split attack, and I will tell you in a second why we call it as such. What is the application-specific rule that we try to exploit here with the hash split construction? The idea here is that the rule that the Bitcoin miners are only able to mine on the block that they have received first. And so if we present two valid blocks to a miner, the miner will select the one that is relayed first, and then we'll start mining on top of that block. The other idea is exploiting something to do with the communication model. So what is the communication model property that we exploit? It is the fact that a synchronous network using which we can relay blocks at different times to subvert the miners from proceeding with their mining process. And the application property that we intend to violate are basically two properties: the common prefix property and the chain equality property. And namely the common prefix property defines the blockchain consistency, and it specifies that two branches of the chain have the last k blocks in common. So again, to the key idea behind hash split attack is that an adversary mines a block and then withhold it. In this case, this adversary in the middle, like between M1, M2, M3, M4, and given that the adversary itself is connected to all of those nodes, it waits for another miner, say for example, in this example, miner M1 to mine a block. And once it receives the block from M1, it relays the block of the adversary to M3 and M4. And when M3 and M4 receive the adversary's block, they immediately start mining on top of that block, which would lead to a fork. And so as a result of the concurrent mining of the two branches of the public chain, you will have that fork, and the concurrent mining would result in violating the property of the blockchain system. Now, this is the high-level idea of hash split. However, to be able to execute this idea, we are faced with multiple challenges. The first challenge among them is that basically we need to identify, because not all Bitcoin nodes are mining nodes, we or the adversary would need to basically identify and detect nodes that are miners, and target them. Moreover, we need to characterize the communication model among the mining nodes and measure the block propagation among them so that we can actually achieve the attack with the target high probability with the least amount of effort. Finally, we need basically to construct an attack that is admissible in the Bitcoin computational model. And so to do so, and to address those challenges, we first formulated the Bitcoin ideal functionality for formally specifying the distinction between the mining and non-mining nodes, and outlined the communication model that preserves the blockchain consistency, and thus the name ideal world functionality. We then developed the crawler in the Bitcoin network and deployed it in the Bitcoin network, through which we detected 359 mining nodes, which is quite a small number of nodes compared to the large number of nodes in the network, about 11,000. And using the block generation frequency of the mining nodes, we estimated the hash rate of each of those mining nodes. Then we measured the network reachability and block propagation patterns of two mining nodes. And our results showed that the mining nodes receive blocks at different times, validating our basic insight and assumption that the network is asynchronous. Moreover, miners with a high network reachability are able to relay their blocks faster than other nodes, which is the other insight that we employ for that tag. So given these measurements and insights, we now present the hash split attack procedure in more details. First, as mentioned earlier, the adversary exploits asynchrony to create a fork and split the miners into two groups, and it starts mining on the branch with the higher hash rate. And if the adversary can maintain a fork for k consecutive blocks, the adversary can then violate the common fixed property. And after violating the common fixed property, if an adversary releases a longer private chain, he violates the chain equality property, win-win for the adversary, lose-lose for the system. And so to sum up, if the fork persists for more than k blocks, common fixed is violated. If the winning chain has more blocks than adversary's hash rate, then the chain equality is violated. And so after creating the initial split, we show all the events that allow an adversary to maintain the fork for k consecutive rounds. Moreover, we also show the events that lead to the fork being resolved in this lower part of, in the blue part of the fork resolves. And then we specify the model, our attack for an adversary with only 26% hash rate, which is a weaker adversary than that of the 48% rate that discussed earlier. We then use a state machine model to compute the long-term probability for violating the common prefix property and the chain equality property. And then our results show that in the current network with the current configurations as measured, the common prefix property can be violated with a high probability of about 3/4, that is 0.74. And the chain equality property can be violated with a probability of 0.83. We also conducted discrete event simulations that indicate that demonstrate the attack feasibility. As well, we deployed the attack countermeasures in the Bitcoin core and released the Bitcoin lockstep that captures the defense. And so this work again is just accepted to ACM-CCS 2021, which is a major conference in our field. And the conference will be held in November. The work is mostly done by my PhD student, Mohammed Saad, in conjunction with another PhD student, Afsa Anwar. And to sum up, the hash split combines the application-specific policies with network asynchrony to create a fork. And adversaries can violate the blockchain consistency and chain equality with only 26% hash rate. And we deploy the hash split countermeasures in the Bitcoin core. And that is quite a success story that we report here. Okay, so moving forward, let's look at the other property that can be violated through the root cause analysis that we uncovered, which is the communication model, and can be used for launching attacks and their possible defenses. So I will now basically present the sync attack, in which we also showed that by exploiting the churn, an adversary can deteriorate synchronization and launch a double spend attack without actually requiring a mining power. And so the idea here we want to discuss through a running example. And so here we show the classical double spend attack proposed by the initial work of proof of work of Bitcoin by Nakamoto. That violates the blockchain consistency property. So let's consider a group of miners like the ones that we have here, and they are mining basically blockchain. Next, an adversary corrupts some miners so as to acquire the 51% hash rate. And now the adversary forks the chain and starts mining on a private chain. In his private chain, he incorporates a double spend transaction. A double spend transaction is a transaction that uses the same input, the same balance, twice for two different outputs, so that both are going to be posted on the blockchain. The merchant who sees the public chain will basically give a product to the adversary after the k blocks, because k blocks is the one that required for confirmation. However, the merchant is unaware that the adversary is mining a private chain which is longer than that on the public chain. And so once the adversary's private chain becomes longer, the adversary can release that private chain. And given that in the Bitcoin, the longest prefix is always adopted in the network, then the adversary will win the game of the block by updating the chain, which is the case in the scenario where the adversary chain with double spend transactions will be adopted. And in conclusion, what you get is a double spend attack launched by basically replacing the public chain with a private chain that is longer, violating the blockchain consistency property. Now, let's take a closer look at the block race model that we have here. The adversary, the probability of double spending, can be characterized by the following equation. It's going to be alpha over beta to the k, where alpha here is the adversary's relative hashing power, and beta is the honest miner's relative hashing power, and k is the gap between the honest public chain and the private public chain mined by the adversary. And here we notice that if alpha is greater than beta, which means the adversary has the 51% hash rate, and the honest miners have, say, for example, 49% rate or less of hashing power, then the double spending attack will succeed with a certain probability, with a probability almost 1. However, if the attack, if alpha is less than beta, the adversary's success probability is going to decrease exponentially as k increases. And so if we look at all the attacks that have been proposed so far in the literature, they are used to relax the adversarial requirements. And we note that those works, optimizations, focus on exploiting network irregularities to reduce the value of alpha and is still successfully double spent. And so the best we have been able to get in our work is the 0.26, 26% of hash power with hash split, which is a big leap compared to the literature that I explained earlier. And we observe that all the prior work stipulate that violating the Bitcoin blockchain consistency requires an adversary to control some mining power. Therefore, we are confined to the environment and attack model where the adversary controls that mining power of alpha so as to introduce and then double spend later on. The idea that we exploit is entirely different. And the question is there other ways to double spend without actually using any mining power? In other words, can the adversary introduce and maintain forks for k consecutive blocks without using any mining power? The answer to the question is procedurally addressed. And so to answer the question, we revisit some findings in our prior work, and we note that the Bitcoin network is asynchronous and block propagation incurs some delay. And so we also note that delay in the block propagation and reception depends on the network out degree, which is impacted by the network churn. From those two observations, we also note that the block can fork naturally if the network out degree falls below a threshold. And based on this illustration that we have here, we can conclude that if the adversary controls the communication model, the adversary can deteriorate the network out degree or increase the block propagation delay. And as a result, instead of an adversary competing with an honest miner, an adversary can basically bid two honest miners to compete with one another, and in a way that the adversary will be able to win through some manipulations. And so we noticed that this observation was ignored in the literature, in all the prior work, particularly in constructing their attacks, and this is what we exploit in this following attack. So again, in this type of scenario, instead of looking for an alpha where the alpha is controlled by the adversary, the ratio of the hashing power controlled by the adversary, that has to be large in order to be able to win the game of block. Here we try to basically bid honest miners against one another unknowingly, so that the adversary can win the game. And so with these insights, naturally, the first step would be to analyze the security implications of network synchronization. We first basically incorporated synchronization in the Bitcoin security model. To that end, we again formulated the Bitcoin idle functionality that incorporates synchronization in the Bitcoin security model. And using the ideal functionality, and we extract bounds on the network out degree and block propagation delay that prevent natural forks and maintain the synchronization. And if these bounds are violated, then the block chain among the honest miners will naturally fork. And next, we conduct measurements to see these weaknesses and highlight them in the practice between October 2020 and December 2020. So consistent with our initial measurements that we conducted in the root cause analysis, we found that the Bitcoin network has a high churn. 9% of the nodes, including all the mining nodes, depart from the network at any point in time. And this observation leads to vulnerabilities in network state, which can be exploited to launch the sync attack. And then if the adversary occupies all of the available connections, slots of the existing nodes in the network, then the incoming nodes will not be able to connect to any existing nodes. And so again, to highlight you the idea here, let's assume that we have a bunch of nodes, and those nodes are reachable nodes, meaning that they are actually accepting incoming and outgoing connections. And so those nodes have a regular path between them and each other. And so let's say that the new node arrives to connect to a few other nodes, will be reachable, departs, no harm happens, adjusting the table. There are other type of nodes that are unreachable nodes. And so those unreachable nodes only make outgoing connections, do not make incoming connections, so they can't serve others. And so they come in, they connect to the rest of the network, they will be able to benefit from the network, they will not be able to benefit the network. Let's say that a bunch of those came in. And so they connect to the network, they will be able to benefit from the network, but they will not be able to propagate anything to the network. They will not be giving the network anything. And so let's say that somebody else came in, like some other benign node came in and connected to those nodes with this capability. Then those nodes, let's say that they were fed by they were connected with some malicious node, a malicious node that actually going to be like allowing incoming and outgoing connections. And so those nodes, the ones in the blue, will be only fed the information provided by that of the red nodes, the dark red nodes, which are the malicious nodes. And so as a result, if you create this kind of larger connection, if you basically map the network and able to connect to those all those nodes that are connected to only unreachable nodes, then you will be able to create a fork. And the fork is only created because those nodes here are mining in one direction, those nodes are mining in another direction, and they are only fed information by the adversary. The adversary, in that sense, completely controls the communication model in the network of the arriving nodes. And so I think in the interest of time, I'm going to skip over this very quickly. And so as a result of this kind of high-level idea, you will be able to basically partition the network without having to have any mining power. The only thing that you exploit is the fact that there are some reachable nodes and unreachable nodes. So the procedure is very quickly, basically in Bitcoin, the default incoming and outgoing connections are set to 117 and 8 respectively. And given a network of a size of approximately 11,000 nodes, the number of reachable connections slots are about 1.2 million. And if the adversary has to occupy all of those connection slots, then you need several thousand IP addresses with a cost of about $4 million. Thus, the attack, despite being possible, becomes infeasible. However, during the study, we discovered that vulnerabilities in Bitcoin Core that allows the adversary to establish 65,000 connections using a single IP address by iterating over the port numbers that you have shared with the IP address. And so we developed a lightweight script that mimics the behavior of Bitcoin node and occupies all the connections of victim nodes using a single IP address. And so given the vulnerability, we observed that all adversaries can occupy all the incoming connections of the existing nodes using only 20 Docker containers. We basically occupy the 8 reachable nodes to which the arriving nodes connect. And after 11 days, all mining nodes are among the arriving nodes, and the adversary breaks the network synchronization. And as a result, you will be able to create isolation. We able also to split miners, trigger block race, issue double spend transactions after K block confirmations, and release the longer blockchain in the following way, assuming that you have, the original way, you have two groups of miners, one of them with alpha and one of them is beta. And so in one, you will have a regular transaction, the other you'll have the double spend transaction. the one with double spin transaction, the adversary will be able to observe all of this. And so once he sees that there is a competing strategy for the chain with the double spin transaction, he will propagate that to the rest of the network so that it is committed over the ones that are basically does not include the double spin transaction. Adversary can double spin without using any mining power, and estimated cost for this one is below $1,000. So to sum up, and again, this work is not published. We are planning a submission of this work hopefully soon. So again, we propose application-specific attacks and network-specific, countermeasures. And for the application-specific countermeasures, we patch the vulnerability in the Bitcoin core. And then for the network-specific defenses, we show that if the mining nodes can resist the churn, the adversary cannot control their out degree. And so in conclusion, we comprehensively analyze the blockchain systems attack surface by studying application-specific attacks and network layer attacks. And then for each attack, we propose some defenses, countermeasures. Hash split and sync attack are actually new types of attacks that exploit some properties or characteristics that have not been used in the past. And then we empirically measure the network synchronization and find out it is asynchronous, and we look into their effect. And we incorporate synchronization in the Bitcoin security model through those idle functionalities, and our theoretical modeling measurements and attack open new directions for attacks and defenses in the blockchain community. For those who are interested in this area, we have here a bunch of publications. I think we have been very successful in this domain, and in the sense that our group has been one of the one of the only groups that have pushed the boundaries of this work farther. We have had a couple of BIS paper awards on this work. We were able to publish this type of work in ACM, CCS, ICDCS, which are very hard to publish in with kind of a work that looks into new attacks that have been not, using, some ideas that have been examined before. And so, again, those are a couple of the awards that we had for this work. So in conclusion, I would like to really thank my sponsors over the last few years and all the excellent PhD students, postdocs, visitors, undergrads, master students who have been working with me to make this work possible. I also would like to thank the department and the cluster for all they have provided to enable this work.